All right, so
Gang.
we can finally start on the very last lecture. All right, so let's start first talking about some of the components that we were using to build your system. Most of these effects will be negligible for rap, but I feel like it's good to know just in general what would happen at higher frequencies. So the first component that we're all familiar with is the operation of a resistor. So when you think of a resistor, you have like two different types of resistors, right? You have your through-hole resistor that kind of looks like that. And then you have your SMD resistor that kind of looks like that. So you have two types of resistors here. I'm only gonna draw the pad actually. Two types of resistors here. And well, what is a wire? At the end of the day, a wire has some inductance. So when we model a resistor, we model that as, everyone's familiar with just the regular resistor model. And then now we add the inductance of the leads. Since wires have inductance, these pads also are, these contact points on the SMD components also can be thought as like a short wire. So they have some amounts of inductance. Two inductances here to represent the two different types of connections that can be made. And finally, there is a within each resistor, there are particulates, and how it's constructed degenerates these resistances by some type of like dielectric particulates in material, and that could be modeled as some type of capacitance. So you have some capacitor that goes in parallel with everything, right? So you get something that looks like this. Now, here we can describe the system by finding what the impedance looking in to the system would be, Zn. And you guys know how to calculate Zn of components in series and components in parallel, so I'm not gonna go through that and cumbersome you guys. So Zn is just gonna be equal to Ls plus R over LCS squared plus RCS plus 1. By inspection from here, you can tell that the zeros are going to happen at negative R over L, and the poles is equal to negative RC plus or minus the square root of RC squared minus 4 AC 2LC. Right, we get something that looks like that. That's an L. But all in all, we can plot what the graph of this would look like. You can see down there? All right, we can plot what this would look like. And we see that the resistance actually experiences a spike before it encounters two poles. So it first encounters a 0, and then encounters a pole here and a pole here. So in reality, what happens is as your value of R increases, your roll-off actually gets pushed further and further inwards. So at higher and higher frequency operations, you typically don't see massive resistors being used because if you look at, this is just like an example, right? Some frequency, some impedance value. You'll notice that let's normalize all the resistances for now. You'll notice that at larger and larger, you'll have something like that, and then like it gets further and further out. So the smaller and smaller your resistances, the further out you can push it, but there's gonna be some resonance peak due to this LC resonance. But the smaller and smaller resistance you use, the faster and faster it'll get rolled off. So at higher and higher frequencies, you don't want to use bigger and bigger resistances because effectively the particulates that are used to construct the resistor will short out your resistor. And so you won't actually see a resistor at higher frequencies. So that's some effect that you want to be take notice of. So that's for resistors. This eraser is terrible. But so that's for resistors. Now we can go into capacitors. So now we can go to capacitors and how capacitors behave. Again, for the frequency of operation that we see at RAP, this won't become a major issue. But similar to how a capacitor or resistor is, you can see like the through-hole component looks like this, and the SMD component kind of looks like that. We also see, so we have a capacitor here. Now, just like some thought, when you have, let's say, a DC signal going through a capacitor, like let's say I'm applying some voltage across this, some DC voltage, we expect zero current to go through, right? Because this acts like an open at steady state. But is that the case? So no, that's actually never really the case. It might be really small that you can't really see it, but you actually have some parallel resistance, call this RP, that spans the capacitor. And this model is kind of like the dielectric leakage that you have in your capacitance. And typically this is ignored. You'll notice that when you look at spreadsheets and data sheets for capacitors, you'll see this ESR term. That stands for equivalent series resistance. And that resistance is typically seen like here. And that ESR actually lumps both RP and RS together, but RS here is actually representative of like the heat dissipation that you see. So even at super high frequencies, when you expect this capacitor to short out these two nodes, you actually still see some heat dissipation through some series resistance. So you can bypass the dielectric loss, but you can't bypass your thermal loss. And similarly, like how we had leads connecting these capacitors, you'll also see some type of inductance. I guess I can just draw on one side, doesn't really matter. All right, you see some inductance like that. And so I could go through the math and give you guys the equation for, I guess, yeah, I'll give you guys the equation for Zn. Just the final result of just what it'd be look like, just look into the port. You would see something that looks like this. I think I looked at it this way, but it shouldn't matter. You get RPLC S squared plus R S RP CS plus LS plus RS plus RP, all divided by RP CS plus 1. Now this probably doesn't really mean much. Again, I can write down the zeros and the poles, but I don't think that's really necessary, right? You guys are never going to probably use this equation anyway. I think the most important thing to get out of this equation is just what the characteristics of a capacitor would look like. So normally, when you graph the Zn, Zn of this, what do you expect this plot to look like for an ideal capacitor? It would be diagonally going down, right? So it would look something like this. So in actuality, how many poles and how many zeros do we have? 2 zeros and 1 pole. So we first encounter the pole, and the first pole is actually like very close to DC. And what you actually see is you eventually hit some resonating point, you hit a 0, and you hit another 0 like that. So whether or not, depending on how close these poles are, you can either see a really big dip, or you can see like some type of flat region for your transfer function characteristics. But you'll notice that at super high frequencies, your capacitors can like sometimes it's not purely just going to be the inductor that's overwhelming it. The ESR, this is not a purely linear component. This resistance actually changes as well. But at super high frequencies, these tend to dominate, and you won't actually see the capacitor that much anymore. So that's your capacitors, right? Now the final element that we're going to discuss is an inductor. And I think this one's actually the most intuitive to see what happens. So let's say, I'm going to actually draw this kind of okay-ish. So let's say you have some type of inductor that looks like that, right? It's a coil of wire that wraps around itself tightly to create some type of inductance, right? But at the end of the day, what is a capacitor? Essentially just two plates of charge, right? But you'll notice that between here and here, there exists some capacitance. Between here and here, there exists some capacitance between these coils. And so you actually have an inductor with some parallel capacitance that goes across the inductor due to this effect. Does everyone kind of see like how this capacitor kind of arises? And as we all know, a wire is a conductor, and a wire has some resistance itself. So we actually see some resistive value here. All right, so we see L, an R, and a C. Now, for the sake of completeness, I will write Z in for this as well. Zn is equal to Ls plus R, LCS squared plus RCS plus 1. You'll notice that this equation and that equation are very, very similar, if not identical. That's because I lumped these two together, right? Because two L's in series can be just 2L. But with that being said, that kind of gave away the answer. An inductor will also act like an inductor for only a certain amount of frequencies before the capacitance takes over, and you basically short out the inductor. So those are kind of like some of the effects of resistors, capacitors, inductors at higher and higher frequencies. Does anyone have any questions? All right. I think for sake of completeness, I will go over a little bit more about some of the effects of capacitors. So everyone's familiar with the dielectric constant K, and that is defined to be epsilon over epsilon naught, right? So what does K actually represent? What happens if I have a large K versus a smaller K? What happens to the value of capacitance? Yes?
Oh, whoops, I was going to answer it.
Go ahead.
Sorry, like the amount of area you need changes based on the K, like to have the same capacitance.
Let's say I have maybe like 1 micron cubed to work with. If I have a higher K versus a smaller K, what happens to the value of capacitance?
Goes up.
It goes up.
Yeah.
So you can think about like K as like the density of like, you can think about like how dense this capacitor is. So the higher K you get, the more capacitance you get per side for amount of thickness between the plates. Now, there's always a trade-off in engineering. If I make K really, really large, right? What's a downside you can think of if I make K really, really big? So I want to pack like 1 microfarad or 1 millifarad in like a really small package. What's the downside of that? Yeah.
That's heat dependence.
That is one of them, but the bigger one is temperature variation. So,
Wait, I'm tweaking.
I guess I thought you meant like heat dissipation, but
No, like heat dependence isn't like as ambient temperature goes up, it like messes with it more.
yeah, so it changes quite a bit. So you don't want to use too big of a K because of that reason. It'll deviate a lot from what capacitance you expect. And then, so I guess like the last thing I have is quality factor. So quality factor of a capacitor is typically modeled as XC over ESR, equivalent series resistance. Similarly, the quality factor for an inductor can be written as XL over RS. That doesn't seem right.
Isn't there like
Should be the other way around.
Q versus the not loaded Q?
Should be the other way around. So this, if you have a really big quality, if you have a really good quality factor, ideally infinity, that means RS is small, so this is right. This might be flipped. This, I'm pretty sure, is this. For a high quality factor, ESR should be ideally infinite, and you'll see it open here. Oh wait, no, this is right, this is right. Sorry, this is right. ESR is equivalent series resistance. Normally when we think about quality factor for capacitor, you think about the capacitance in parallel. But ESR, which is what you give in a data sheets, is actually in series. That's why it's like this. Does anyone have any questions now? That's kind of like all I had for this.
I was going to ask for the non-idealities, just like for phases, does that introduce any issues? Or it's mainly looking at
You might see some phase difference, but capacitors normally introduce 90-degree phases anyway. Similar to inductors, you'll also introduce a 90-degree phase. But as your regions get more, how do you say, inductive here, right? So normally when you see a pole, what happens to the phase diagram? It goes down, right? Down by 90 degrees, and this kind of goes back up by back up to 0 and then back up to 90-degree phase, right? So you will see a phase shift here, right? The system's well behaved, so I'm pretty sure both of the zeros here is actually on the left-hand plane, so you won't actually see any like crazy right-hand plane zeros. And now we're gonna completely switch gears now and go into some nonlinearity stuff, and that's where all the mixers and all the amplifiers and all of that will kind of hopefully make a lot more sense. Wow, this eraser's. Do we have a better eraser? Huh? There's a back of the board. Nah. Well, it's okay, we'll deal with it. Give ourselves a little bit more room. Yeah, this eraser is definitely going to be gone by the end of this lecture. It's already like ripping off. But we'll make it happen. Okay. For the first topic I'm going to talk about is harmonic distortion. And actually, you guys kind of already seen this, if you guys remember in if you guys remember if you guys remember in mixers lecture, right? If you have some type of system, call it, I'll just call it H actually. Call it H. Feed it X, you get Y. A system can be modeled as A1X1 plus A2 A1X A2X squared plus A3X2. Right? You guys remember this? Now, if we let the signal in be some A cosine omega t, then we know that Y you would get A cosine omega t plus A squared cosine squared omega t plus dot 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 dot, right? And then if you guys remember, this has a frequency of, well, we know that omega equals 2 pi f, right? So there's going to be some frequency at omega here. there's going to be some frequency at 2 omega. Why is there something at 2 omega?
Square.
Yeah, so it's squared, but if you do the power reduction,
Yeah.
it's you get the 2 out, and then you keep going, you get some 3 omega, blah 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 blah. You get a lot of that, yeah. So when that ends up happening is, you'll get a bunch of terms with different values on them, but essentially, this states that the important thing that you guys need to get out of this is, for a large enough input, because what happens if x is really small? These terms kind of go away, right? Like 1/10 squared is 1/100ths, and then 1/10 cubed is 1/1000. So these terms kind of go away. But if x becomes large, then we start seeing harmonics of our fundamental frequency. So in RF applications, actually, in terms of like when we receive something or when we transmit something, harmonic distortion isn't usually a big issue because we can always typically filter it out. It actually shows up. Most of the things I talked about previously doesn't show up in a RAP system, but this actually does show up in a RAP system, and you guys should have seen it before when you guys designed your oscillator, when you guys designed your mixer. You guys should have seen, particularly your oscillator, if you guys took the FFT of it, you should have seen peaks at 4 meg, at 8 meg, at 12 meg, at 16, and so on and so forth. And it gets the strength at each frequency, at each of those harmonics decreases. And that's just because of like the power reduction formula. You see it's a squared over 2, and then if you do the trig out, the third equation is the third one would be, I should not have done a squared. It should be, yeah, it'll be a3. Sorry, this is squared because I put this through the system. It'll be a. There should be some alpha 1, alpha 2. That's what I forgot. It'll be a to the cubed alpha to the third divided by 4. If you did the math out, which I won't go through again. But it gets smaller and smaller and smaller, right? And that's just because these alpha terms get smaller and smaller and smaller. And that's really the Taylor series expansion of whatever your system is. And so normally, as I was saying, it doesn't. This isn't a big issue in RF applications because, and think about like, let's say like Wi-Fi, 2.4 gig. The next harmonic is 4.8 gig. That's easily filtered. Yeah, you can easily filter that. It's not like a really tight constraint. You know, they're not really close to each other, so you can always filter it out. So it's not a huge issue. But can you guys think of a component that would become an issue for us in mixers? I guess that actually answers my own question, but there you go. It happens in mixers. And yeah, so that's one of the non-idealities or nonlinearities that I feel like you guys should know about. The next one that comes hand in hand with this is called gain suppression. There's actually not really, that I know of at least right now, figure of merit to describe this. This just kind of happens. But there is a figure of merit for gain suppression. So what is gain suppression? So ideally, when you have a system, right? When you have a system, you have some X input and some Y input, right? Ideally, what happens to a linear system? If I apply a linear system, what do I expect this graph to look like? Straight line. How so? Like that. Okay, perfect. So you expect something that looks like that, right? I apply some input, I expect to get some output. Think about like without all this term, right? You get some linear expression. Now, with this, as X becomes larger and larger, these terms become more and more significant. And it turns out most systems are compressive. So it doesn't matter really what sign alpha 2 is here, but alpha 3 and alpha 1 typically have opposite signs. And in most systems in general, A3, I guess. And yeah, most systems in general, these two have opposite signs because most real systems, if not all real systems, are compressive. I can't really think of an example of a expansive system or a system that blows up. Because if you think about it, if this and this are the same sign, then you just see this will go up to infinity, right? It'll go, as x gets larger and larger, your output gets larger and larger. That's not the case. So what ends up happening is you'll see something that kind of like looks like that. Right, so ideally you'll see this, but in actuality you see that whatever I feed in, I actually don't get what I thought I would get at y. So there is a measurement that we use in RF applications called the 1 dB compression point. Now what is that point? That point is basically when the actual and ideal characteristic of a function is different by 1 dB as such. So that's gain suppression, that's the compression point. And the suppression or gain suppression point, you can actually solve for this point. Let's say it's here. What amplitude gives you that point? So I'll just call this A in, and we'll just, and this is actually approximately 0.15 times the absolute value of alpha 1 over alpha 3. So if you're able to know the coefficients of your system, you can actually solve for when your system experiences gain suppression or gain compression. Does anyone have any questions? Yes.
For like harmonic distortion, I see the term like total harmonic distortion like come into play every now and then. What does that mean?
I'll get to that.
Okay, cool.
Yeah. Your total harmonic distortion, like, yeah, I think I'll get to that in a bit. Yeah. Does anyone have any other questions across these two? Okay. So, so there's another phenomenon called, I should have wrote this here actually so I can have more room to work with. Every single time I write alpha, I mean these variables. I'm just going to use them kind of like interchangeably, but there's also, since we talked about gain suppression, the concept of desensitization. So let's say I have on the frequency diagram my desired signal, and then I have some I have some desired signal and I have some blocker like that, right? That just so happens to be right in where my carrier is, right? So this is my desired signal, and this is the blocker. Like, we can deal with this, right? Well, we have to do some work to fix this, but we notice that we have some spectrum of blocker that's blocking our desired signal here. Now, what happens when this goes through a system that is, what happens when this is so large that it goes through a system that experiences gain suppression? What will happen is, well, just looking at the graph here, right? If this is really far in here, it actually won't get amplified at all, right? Because you're suppressed already. Whereas this signal, if it's down here, it will get amplified. So your SNR, or your sensitivity had to go up, your SNR get worse, right? Does that kind of make sense?
Yep.
What would a blocker look like?
Like any type of interference.
You're just like
that you see.
in the channel or something, or like
Yeah, it's like,
where's that at?
I mean, whenever you send something like, let's say that, I'm trying to communicate wireless to someone else. Other people can also use that channel, right? So that could cause this, but a main cause of this wouldn't really be that. We would really see this more in a duplexer system, where you have a duplexer that switches I want to transmit versus I want to receive. Typically, when you think about what type of power that you're transmitting, is going to be significantly larger than whatever you're trying to receive. And if you put them too close to each other, then you have this issue, right? Because you're transmitting and receiving at frequencies that are comparable to each other. Forget that. That's called desensitization. And you can kind of quantify this effect. So if I let x of t, which is a signal going into the system, and if I let that to be a1 cosine omega 1t plus a2 cosine omega 2t, right? Just the sum of these two. It's not really a span here, it'd be more like an arrow now that I'm drawing, right? Since it's only at one frequency, but you can think about it like it's spanning across different frequencies. This is just like a simplifying effect. We run through that into that expression here, and we'll notice that on our fundamental, I'm not gonna bore you guys with the math, as per feedback. We get alpha 1 plus 3 halves alpha 3. We get this term, right? Where omega 1 is assumed, omega 1 is assumed to be the information that we care about, right? So if omega 1 is the information that we care about, that means A1 is much smaller than A2, right? Sorry, A2 is the information we care about, A1 is the blocker, right? So if A2 becomes really, really large, you can see how this kind of overwhelms. No, sorry. If A2 becomes really large, this goes to 0, right? Because alpha 3 has opposite signs of alpha 1. So if A2 becomes really large, aka, I meant A2 is the blocker. I'm gonna write that down so I don't keep messing that up. Right? If your blocker becomes significantly large, aka if this signal becomes large, because this alpha 3 has an opposite sign, you'll eventually just kill this term. And therefore, your entire system is desensitized. That making sense to everyone? Cool. Now we'll go over the effects that we kind of wanted in mixers, but in general, you don't really want. So I'm gonna go over that real quick. I think I can erase this. I feel like this is also really good to know how to measure in type of software. It's good to know. I've been asked this before, like how do you characterize a system? And you can talk about gain suppression and stuff. The whole goal of this lecture is to kind of like clear up some of the idealities or non-idealities from the lectures previously, and to also hopefully like get you guys a better idea of how real world systems and like some real world problems that we see in our systems. That was the intent of this lecture, at least. Okay, so now let's move on. We experienced one blocker, but oh my god, that's terrible. Right, I'm just gonna write the system up here just in case you guys forget. Alpha 1 x plus alpha 2 x squared plus alpha 3 x to 3 plus da da da. Okay, so we have that. Now, let's talk about something called intermodulation. And I guess now I can finally answer what total harmonic distortion is to you. If you remember what we just talked about for gain suppression, right? That means in the beginning, if A is small, right, then you notice that the alpha terms, they normally get smaller and smaller and smaller as you get further and further out in the harmonics. But at some point, the first fundamental harmonic is going to experience gain suppression. Then the second harmonic will experience that gain suppression. And then the third harmonic will experience that gain suppression. And so total harmonic distortion kind of refers to like a lot of your harmonics are now gain suppressed, and you see all the harmonics in your output.
Because the first one's been suppressed so much, or why do we see them more than we did if they're all being?
Well, think about it like
experiencing like gain suppression.
You see it like that, right?
Yeah.
Wow, that is terrible. That is not what I meant.
Oh, it's because all of them aren't like that strong. Like their amplitude is lower, so they're like.
So think about it like this. In the beginning, your fundamental is kind of like has this strength, and then your second, your third, like let's say this is your 3F, 2F, F, right? As you walk along and increase the strength, suddenly all three of your frequencies here are all gain suppressed. So that means they're all going to experience a similar amount of amplification, and therefore you'll see all three of the harmonics at like relatively the same strength in your output signal. That's what's meant by like total harmonic distortion. That makes sense?
Yeah.
Cool. Oh my god. This is insane. Okay. Intermodulation, here we go. Yeah, so this happens when you, let's say you have your desired signal here. And let's say you have two blockers, right? Now, let's say this is F1, F2, and let's say this is like FC for now. Right? If you remember from, do you guys remember kind of like the third order harmonics that you see, what frequencies they are from the mixers lecture? Assuming, you guys do here, you get, you see some of this essentially pop into there, right? Because you get like 2F1 minus F2, and then 2F2 minus F1, blah, blah, blah. You get all of that kind of dumped onto the desired signal of interest, right? So, we get, yeah, like I said, 2 omega 1 plus or minus omega 2, and 2 omega 2 plus or minus omega 1. Let's just call this omega for now, right? But if you think about it like this, which one would this likely be? Would it be 2 omega 1, I guess, minus F2, or 2 omega 2 minus F1? Probably be this one, right? So essentially, when you write out the terms and you throw the x equals a1 cosine 1 omega, the a1 cosine omega 1 t plus a, into that system, at omega 1 you see alpha 1 a1 plus 3/4 alpha 3 a1 cubed plus 3/2 alpha 1 a2 squared at cosine omega 1t and then you get a kind of similar thing for omega 2. I don't want to write it down. But you notice that if we normalize this frequency to the fundamental, so if we normalize this product back to the fundamental of the signal, right? When we solve that out, we get a relative, we call it a relative IM product, like an intermodulation product. And I don't want to bore you guys with the math here, but it is equal to 3/4 alpha 3 alpha 1 a squared. Normally this is measured as a relative term. So we take 20 log of this, and this will have, if we take 20 log of 3/4 alpha 3 alpha 1 a squared, the units for this is dBc. Does anyone know what that stands for? Yeah.
It's like the relative difference between the carrier and whatever you're seeing like back there.
Yeah, so you typically want to see like dBc at however megahertz, or how many, usually it's megahertz, and if you're working with a multi-gig system, how many megahertz away from some center frequency, right? And so this will kind of measure like, this figure of merit, I guess, will measure how much of the IM3 product do you have relative to this. So you can see, like, as you get further and further out, you should go further and further down, right? As you increase your amplitude, your IM product gets stronger and stronger, which is expected, right? So does everyone see kind of how this kind of makes sense? Cool. So now there is another figure of merit that we use a lot, and you've probably seen this term being tossed around, and it's called the third intercept point, also known as IIP3 point. You guys have probably heard this term being tossed around if you've looked up some RF stuff in the past. In general, you can generalize this to IPN, but IIP3 is a very popular one. IIP3 and IIP2 are the most popular one. IIP3 is more popular than IIP2 because typically when you're working with frequencies that are really close to each other, your IIP3 point would be very close to something similar to maybe something like your signal, right? So that's why IIP3 is generally more important. So the IIP3 point is kind of describes the point at which your so when you have two signals like this that are being inputted into your system, right? You can get something that looks like 2F1 minus F2, and you get something called, this is called a spur, right? These two things are called like spurs. Right, you get something that's like close by. When this spur becomes equal to the fundamental, that's when you've hit your IIP3 point. And you can graph that conceptually by saying A in, this is in log scale, this is all in log scale by the way. Let's say you have some signal here. This is referring to the 20 log of alpha 1 A1, right? That's just your fundamental. And then you have another term, remember it's being raised to the third power, so it'll come up a lot faster, right? And this would be 20 log 3/4 alpha third AQ, right? And if you were to extrapolate this, you get a point at which they intersect, and that means that both the powers are equal. And also this is for a voltage quantity. That's why I'm using 20. It was power, 10. I guess I should have made that clear. Yeah, this is for voltage, sorry. You have that. And you can solve for the, actually, now, before I go into that, just for a thought experiment, I have an IIP3 point, which means at some input amplitude, you get such that the spur is going to be equal to the fundamental, right? If you guys remember, as I increase the amplitude, what other effect will happen? It'll be gain suppression. Which one occurs first? What do you guys think? It's a really simple vote, I guess. Who thinks compression point happens first? Okay. Who thinks the IIP3 happens first? Very nice. So it turns out that the compression point will actually occur first rather than the IIP3 point. In actuality, you'll never see this happen in simulations or in real life. What you'll end up seeing is something that looks like this. And so what simulators do is they extrapolate what this linear relationship will be like and find the point where they intersect, and it'll tell you what that point is. But in reality, you'll get compressed before you reach that point. You can solve for this. You can essentially solve for this by setting this equal to each other. Right. We solve for this in terms of, I guess I could go through this derivation. It's really short. We know that AIIP3, I guess I didn't really tell you, but as this, right? That's just a given formula. You can refer to some textbook if you guys want to figure out how that's derived, but I'm just gonna use this for now. And if you guys recall from AN, the 1 dB compression point occurs at root 145 alpha 1 over alpha 3, right? If you were to normalize the IP3 point to the 1 dB point, you'll see that it's roughly 4 over 3 times 0.145, and this is roughly 9.6 dB. So what does that tell us? That tells us essentially like this IIP3 point will occur, or this gain suppression point will occur this much earlier than the IIP3 point, right? You just multiply this out to this side. IIP3 point is actually this much further, right? Does that kind of make sense?
Yep.
Cool. Okay, so IIP3 is 9.6 dB higher than suppression point. And so, yeah, that's pretty much it for that.
Call it the, sorry to interrupt you, dude.
Go ahead.
Do you call it the third intercept just because it's like the third order, like?
Yep, exactly. So you call it because it's the third harmonic, right?
Okay.
Because it's 2F1 minus F2, and I guess 2F1 plus F2, or 2F2 minus F1. You can have this exact same analysis. Obviously, these numbers won't apply for IP2. It would just be for F1 plus, minus F2 and F2 minus F1. Yes.
So between IP2 and like the compression point, which one occurs first?
The compression point will always occur before the IIP2 and IIPN in general.
Does it just occur like earlier or later based on whether it's IAP2, IAP3, or like, you know, a setting? There's always like.
I don't know if like there's like some relationship like, oh, IIP3 will compress slightly earlier than IIP2, like something like that, if that's what you're asking. But in general, I can claim, or I guess I could say that IIP points, or just intercept points, will occur typically later than your compression point. I'm actually like, now we can take a little break. Yeah, we can take a little break. Okay. Hopefully I upload like the last 2 lecture videos. I gotta figure out how to do that YouTube thing. I like can't upload lecture 4 because lecture 3 took up like 14 gigabytes of my 20 free gigabytes on on Google Drive. So I can't just upload the next one straight into my Google Drive. So yeah, that's awesome, isn't it? Anyways, let's talk about I should say nonlinear systems. Just intuitively, what do you guys think would happen if I have a string of like a set of systems, right? And I needed one of them to be nonlinear. Which one would you want to be nonlinear? Let's say I have a set of like, let's say I have a 5-stage network. Which stage would you guys choose to be nonlinear? Yeah, intuitively, the last one, right? And your intuition would be correct. But we would want to give a little reason for that. So let's let y of 1 equal to alpha 1 x of t plus alpha 2 x squared of t plus dot dot dot. And then let's let y2 equal beta 1 y1 of t plus beta 2 y2 t dot dot dot. And what this is actually saying is like, I have 2 systems, I plug in x, I plug in y1, I get y2, right? Now, I could be a menace and replace x of t with, you know, a cosine blah 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 blah, and do all of this math out for you guys, and I'll probably stand here for like 25 minutes, probably longer, but I'm not going to do that. So the AIIP3 point can be given as, if you guys remember in the first answer, it was 4/3 and then absolute value alpha 1 over alpha 1 over alpha 3. No, alpha 3 over alpha 1, right? It was alpha 1 over alpha 3?
I didn't want to say no.
No, it was alpha 1 over alpha 3. Anyways, this would actually be alpha 1, beta 1, alpha 3, beta 1 plus 2, alpha 1, alpha 2, beta 2 plus alpha 1, beta 3 cubed. Right, if I only consider the first three terms. Right. Do some manipulation, you get something that looks like this. If I invert this and square everything, I get something that looks like I think this little derivation is pretty important or pretty good to see. Right, if I invert this and square everything and then decompose it, I get something that looks like this. Does that look familiar at all? Like a little bit familiar? At least, does this term look familiar? So this is actually equal to 1 over AIIP3 of the first system squared, because there's no square root. And then we can see that this is also multiplied by this, right? And so you can write it as alpha 1 squared over AIIP3 comma second system squared plus dot dot dot. Now you might ask, what about this term? Turns out we can just say this is approximately equal to that instead. And this is the total AIIP3 squared term. And in general, this goes on again with alpha 1. I can do one more term just so you guys can see the trend. Go alpha 1 squared, beta 1 squared over AIIP3 of the third stage squared plus dot dot dot. Right, actually there's no absolute value. And so this can go on forever. Now, if you guys notice something, you have to eventually invert all of this, right? So as you get further and further down the line, everything kind of, like the gain that you see at the first stage is going to be the biggest. So more nonlinearity is going to be contributed by this stage because it's larger, and then third stage is larger. So the further down you go in stages, the more nonlinear you get, and this is kind of the relationship that shows it, right? So that's that. I mean, you guys kind of already got it intuitively, but this is just kind of like show like each time you go through a next stage, it's kind of a little bit intuitive. It kind of increases by just the gain of that first stage. So this shows a certain amount of nonlinearity. This will show now the gain of this nonlinear at the next term, and so on. Now before I go into, actually I will mention a little bit about noise. I'm not going to give you like a full blown explanation about everything about noise because that's a whole like 3-week thing on a class. But just to go over some very basics of noise, let's say you have some transmitter TX. That's not how you draw an antenna. That's also not how you draw an antenna. There you go. TX and some RX, right? And so the last stage of here is called the power amplifier. I don't think I called it that. I know for sure I didn't call that because someone told me that. But the last stage you guys will design in the transmission stage will be a power amplifier, just a really large amplifier that amplifies your signal by a large amount. Typically in a system, most of your power, a lot of your power actually goes to the power amplifier. In fact, in your smartphone, around 40% of your power consumption occurs because of this guy. And the reason for that is, I guess in general, just like a general question, if I had some system, some MOSFET, let's say some MOS amplifier or some sort. If I want to make it more linear, let's make like the most basic device, like something like this. If I want to make this more linear, what do I have to do? Or let's say, you know what? I'm just gonna call this a black box. All right. If I want to make this more linear, I pump more current through it. Right, I make GM better, right? So that's why you want to pump more power into it to kind of make the system more linear. And linearity is super, super, super critical because as it travels through this medium, in classes you'll learn that it gets attenuated by a term of 1 over r squared. But in reality, because of all the interferences of it bouncing everywhere and blah, 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 it's actually closer to 1 over r to the 4th. So you're actually seeing a huge amount of attenuation here. So the power amplifier can maybe output something like hundreds of milliwatts. Once you get to here, you're looking at the regime of microwatts. You're looking at a very, very small signal here, right? And so for practical purposes, your receiver, there's gonna be some noise in the channel as well, right? There needs to be some, what we like to call sensitivity. This is a figure of merit for your receiver. And it basically describes how sensitive does this receiver need to be to detect your desired signal of interest. And that's basically as far as I want to go in terms of noise. There's a lot of different other things that can affect your sensitivity, like your IM products, how much SNR you need, how much noise figure your circuits succeeding after that needs. But if you guys are interested in that, consider taking 215C at some point. Last thing I want to that I want to talk about before I wrap this up is, since we kind of talked about, what do you expect when you cascade a bunch of nonlinear systems, right? Let's say I have some system, a bunch of systems like this, and I have the input here. I guess I could just saw any input here, right? And this contributes, let's say, some noise, let's just call it F1, and this contributes F2. And let's say there's some power gain 1, and what power gain, actually, here's a quick question. Is power gain the same as voltage gain? How is it different? Anyone? You got it?
Okay, fair enough.
Okay.
Like, the matching matters. So it's not just like how large of a gain can you see in voltage from side to side, but also how much of the power can actually be like transmitted to the load on like block to block or system to system or antenna to antenna. Like, so you need like correct matching.
So when is power gain equal to voltage gain?
Good question, actually. Shoot. Power gain equal to voltage gain. I'm just thinking about like the I squared R. Like,
Yeah, so
I squared R versus IV, like if you just like maybe equate that out or something.
Yeah, so I think I talked about this at some point, but let's say like voltage gain versus power gain, right? Voltage gain is, or I guess I can talk about just power gain. Power gain is V squared over RS over V in. V out squared over R out, right? And so when RS is equal to R out, you get V in squared over V out squared, right? And so this is basically equal to your, I should have wrote V out on top and R out, V in, R in, out, in. And the reason why you see, normally this is talked about in log scale. So this is just equal to V out over V in squared, right? So if you take the log of this, like the 10 log of power gain is equal to the 10 log of the voltage gain squared. Bring the 2 in the front, and that's where you see the 20 log AV come from, right? So they're equal when RS is equal to R out, which is what you're trying to say when you're in match. Right. Anyways, back to this main point. Let's say I have a bunch of systems that generate some noise, and each of them have some power gain. Right. Now, if I want to reduce the total noise at the output, right? Which system should I minimize the noise of? The last system or the first system? First one, right? And I guess like intuitively that kind of makes sense, right? You have less noise here, then you're gonna keep amplifying it. You're gonna amplify by slightly less, right? Versus if you have a lot of noise here and you amplify it again, and you got a lot of noise. So in general, because I don't want to go through a massive evaluation, your total noise factor, I'll explain what noise factor is, I guess. Your total noise factor is equal to F1 plus F2 minus 1 over the power gain of 1 plus F3 minus 1 over the power gain of 1 and 2, and so on and so forth. And so you'll notice that your noise factor seen here actually gets suppressed by further stages by that gain itself. So the further forward you get your chain to have, this is where the first circuit is usually LNA. This is where you usually want to like make sure you minimize the amount of you minimize the amount of noise contribution in your first stage, and then you want to try to maximize your gains for the future stages to minimize your noise figure, right? So this is why the LNA is a hard block, because you want a lot of gain on the LNA, but you want low noise, because if you have a lot of gain, then every subsequent stage after that will see that gain being see noise getting suppressed by that gain. And also, you want low noise because it doesn't get suppressed at all. And I guess really briefly what noise factor is. Noise factor can be just seen as the signal at the input over the noise at the input over the signal at the output over the noise at the output. That's just about it. And you can see that normally noise gets worse and worse, right? You can't you don't usually get I can't think of a time when you get, I mean, there is times, but usually your SNR, your output, is usually worse than SNR, your input. I think I flipped this actually. I might need to check back on this, but your noise factor should always be greater than or equal to 1, because the best you can do is match the SNR of your input. You can't get better SNR than what you have at your input. So that's essentially what I want to go over today. It's kind of just like the high level overview of everything. Now hopefully like the reason why you can't have super large gain in a common emitter amplifier kind of makes sense. Hopefully like when you, even if you bias everything correctly, when you have a really large swing, you're gonna see all those effects that I talked about. And if you guys, now I guess I can ask you guys this question, since now you guys know all about this nonlinearity stuff, which is a quick question for you guys. Maybe this will finally make sense. If you guys have, I don't know how many of you guys have done Module 3 yet, but for those that have started Module 3 or are currently doing it or have completed it, you'll notice that your mixer has 3 ports. You have your IF, RF is for up conversion, LO, right? We say that we want LO to be large. Why is that? I know I said to turn on the diodes, right? But why do we want LO to be large? Think back to this. Why do we want LO to be large? Or I guess, why do you want LO to be, well yeah, we just in general want to be LO to be as large as possible. Think about what happens, assume we're not gain suppressed, but think about what happens to here. I guess it doesn't really matter even if we're gain suppressed, but think about what happens at these terms. Think about when we have the mixer, right? The input to the diode is some x1 of t plus x2 of t, right? You want it to be large because you want this term to be large, right? Because if this term is large, then you'll be able to get your f1 plus f2, right? Now, why do I want IF to be small? Yeah.
So the third order product isn't an issue as much.
In general, you don't want any of these products, not just third order.
Oh, okay. Yeah.
In IF, for IF port, you want, essentially, we want IF looking in to be a linear system. You want LO looking in to be a nonlinear system. In general, for a mixer, right? Because you don't want your IF to get distorted. You don't care if your LO gets distorted, right? And then at the end of the day, you'll have some output that you filter out. Hopefully that kind of makes sense now, why we want LO to be large and why we want IF to be small. We want it to be small because we don't want to see this. We want this to be large because we want to see a lot of this, right?
If IF is super nonlinear, is that like that's your carrier, right?
Yeah.
You're messing up the information on it, right? Or like potentially.
Yeah, because
Okay.
you don't want to mess that up. Yeah.
Okay. And then the LO, we're filtering it anyway, so if it is distorted, you're like more okay with that, or what's?
Well, no,
what's
it's because
that?
like when you add these two signals together, right? When you have A1, when you have A IF cosine omega IF T plus A LO cosine omega LO T, right?
Mm-hmm.
You pass that through this, right? This is much smaller than this, right? When you do the whole mixing thing, you also don't want any of this to be essentially, you don't want to see those ion products too much either. Because think about like, if both of these were large, then remember I can't think of the equation off the top of my head, but the third order product will have like some a to the third term, right? And stuff like that. If this and this were large, then your spurs will also be larger, right? Than the values that you don't want. Your third order values, not your second order values, right? Your 2F1 minus F2 and 2F2 minus F1. And if those are comparable, you can think about like just a system like this. If you have, for small IF, you'll see something maybe like, actually you won't see this, right? But because it's isolated. But let's just pretend it's not isolated for now, right? If you want, if you have IF and LO really large, then this will also be larger, right? And so now a filter that is normally like this, let's say you wanted for some reason, let's say your desired signal of interest is somewhere like here. Normally a filter for like this would have been able to capture it, but now since your sparse products are bigger, you actually might see that still we got. Right, there you go. Anyone have any other questions?
How is noise figure related to noise factor?
How is noise figure related to noise factor? Oh, this. So, yeah, noise figure. Noise figure is just I should be I'm blanking on this, but it should be 10 log of noise factor.
Okay.
Yeah. Let me check if it's 10 or 20 actually. But I'm pretty sure it's 10, but I don't want to mislead you guys. Yeah, I'm pretty sure it's 10, but I can check up on that and get a idea.
Power of the signal over power of the waves. Yeah.
Yeah.
If that is greater than or equal to 1,
Mhm.
should it be input over output? Because SNR of the input should be higher.
Yeah. That would make sense. Now I see why I wrote that in the beginning. Good catch. There you go. Wait, I did not even change anything. I'm bugging. Hold up. There we go. I'm bugging. So that means for noise figure, actually, what's the lowest noise figure I can get? 0. Exactly. So don't get confused when talking about this or that. When you see like noise figure of like 900 milli-dB, that's actually possible because it's a noise factor that can't be less than 1. It's not a noise figure. Yep, that's pretty much the end of this lecture. Yeah.